Hello students. So today's class is on Fourier transform. Previously we have our lectures on Laplace transformation and today's topic is Fourier transformation. As you can see that we have Fourier sine transformation, Fourier cosine transformation and Fourier complex transformations. Now, Fourier sine transformation can also be divided into two parts. One is for an infinite and the other one is a finite term. So, the infinite Fourier sine transformation can be written as let a function fx is defined such that x lies between 0 to infinity. So this is the Fourier infinite sine transformation or infinite Fourier sine transformation, the first part. Now for a function fx, if it is defined as x lies between the limit 0 to infinity, then the infinite Fourier sine transformation can be represented as Fs. So S stands for sine. Fsn, it is a function that equals to integral 0 to infinity capital Fx then sine nx dx, where n is an integer. So this is the infinite Fourier sine transformation. Here fx, that is capital Fx, is called as the inverse Fourier sine transformation of Fsn. So if we want to have the value or if we want to calculate this capital Fx, then we have to go through the inverse Fourier sine transformation, and that will be capital F of x that equals to 2 by pi integral 0 to infinity now Fsn then sine nx dx. So these are the two values. These are the two values for the infinite Fourier sine transformation. So here we have defined the function f of x. It is a function f of x which is where x lies between 0 to infinity. Then the infinite Fourier sine transformation, that is Fsn, will be given by integral 0 to infinity capital F of x sine nx dx, where n is a positive integer. And now if you want to find out the value of capital Fx, we have to execute the inverse in Fourier sine transformation, and we have capital F of x equals to 2 by pi integral 0 to infinity then f of s, that is the sine transformation value, into sine nx dx. So these two definitions are for infinite Fourier sine transformation. Now let's move on to the finite Fourier sine transformation of a function fx such that x lies between a range 0 to L. So now this is the infinite Fourier sine transformation. So this is the infinite Fourier sine transformation, and now let's move on to the finite Fourier sine transformation. So here the function f of x is given in such a manner that x lies between, let 0 to L. So there is a finite range of values within which x lies. So now if Sn, that is the sine transformation or finite Fourier sine transformation Fsn, it will be given as integral 0 to L. So the limit is from 0 to L, then f of x sine n pi x by L into dx. So that is the finite Fourier sine transformation of a function capital F of x, where x lies between 0 to L and it is denoted by small fsn, where n is again a positive integer and is defined as fsn equals to integral 0 to L. So that is the limit in which x lies. So the limit will be integral 0 to L capital F of x sine n pi x by L into dx. Now in case L equals to pi, if L equals to pi, then Fsn will be, just put the value of pi in place of L, and we will f of x sine. So if we put L equals to pi, then we have sine nx dx. So we have sine of nx dx. So here we have defined for the finite Fourier sine transformation, we have defined the range in two manner. One is when x lies between 0 to L, and the other when x lies between 0 to pi. So when x lies between 0 to pi, the function becomes, of the Fourier sine transformation becomes Fsn equals to integral 0 to pi capital Fx sine nx dx. But remember, this is actually the general form, where Fsn equals to integral 0 to L f of x into sine n pi x by L into dx, and the special case is when L equals to pi, then we have this value of Fsn. And the inversion formula, that is capital Fx, should be given as capital Fx here capital Fx equals to 2 by pi, and then integral 0 to pi, then small fsn into sine nx dx. Okay. So this is all about Fourier sine transformation. We have divided Fourier sine transformation into two parts. First part is the infinite Fourier sine transformation, where a function fx is defined in such a way that x lies between 0 to infinity, and for that the sine transformation Fsn equals to integral 0 to infinity capital Fx sine nx dx. And the inverse Fourier transformation, that is, if you want to know the value of f of x, then f of x equals to 2 by pi integral 0 to infinity Fsn into sine nx dx. So this is the infinite Fourier sine transformation, and then we have the finite Fourier sine transformation, where again a function f of x is defined in such a way that x lies between a finite value, that is 0 to L. Now if x lies between 0 to L, the Fourier transformation becomes integral 0 to L capital Fx sine n pi x by L into dx, and the inverse Fourier transformation, Fourier sine transformation should be capital Fx equals to 2 by pi integral 0 to L, then Fs n sine n pi x by L into dx. In case of L equals to pi, if the limit of x, if the range of x is between 0 to pi, then just put the value L equals to pi in this general form, and you will have Fsn equals to integral 0 to pi capital F of x sine nx dx. Okay? Is it okay? So let's have some examples for infinite Fourier sine transformation and for the finite Fourier sine transformation. So firstly, find the sine transformation of, the question should be given as this: find the sine transformation of e to the power minus of x, e to the power minus of x. So here the function f of x is given as e to the power minus of x, and if this is the infinite sine transformation or infinite Fourier sine transformation, then we have Fsn that equals to integral 0 to infinity, then the function itself, that is e to the power minus x, then sine nx dx. Okay, so this will be the formula. If otherwise mentioned, then the limit of x should be given, or you have to, if the limit of x is not given, then you have to take it as that infinite Fourier sine transformation. So I have taken the limit, or the range of x is from 0 to infinity, and for the infinite Fourier sine transformation definition or property, we have Fsn equals to integral 0 to infinity e to the power minus x sine nx dx, and for this integral you can put the integral value as e to the power ax sine bx dx. You can find it that there is a standard form of integration, that is e to the power ax sine bx dx. So using this form, using this value or this form of integration, we have e to the power minus of x 1 plus n square into minus of sine nx minus of n cos nx, and the limit is from 0 to infinity. So you can put the particular value of the integral, or you can execute this integration by using the by parts method. Now putting the limit itself, we have that equals to n by 1 plus n square, by putting the limit infinity and 0. So that is one example of the infinite sine transformation. Now let us take the inverse sine transformation. And let us find out the inverse, number 2, the inverse sine transformation of e to the power minus of lambda x. So the function is given as e to the power minus of, sorry, not x, let it be n. So the function is e to the power minus lambda n. So to get the value of f of x, we have to find out the integral, that is 2 by pi integral 0 to infinity e to the power minus lambda n, then sine nx into dn. So the function is given as n, so the integration should be done on dn, and again by using the same integration form, we have the value, after putting the limit, we have the value of 2 by pi into x by lambda square plus x square. So that is just by calculating or by substituting the values of the limit, upper limit and the lower limit, and this is the way we have to calculate, we have to find out the Fourier transform or the inverse Fourier transformation. Okay. Is it okay? So now let's move on to example number 3, and in example number 3 we are going to use the finite Fourier sine transformation. So example number 3. So find the Fourier sine transformation of fx that equals to x such that 0 less than x less than 2. So here the range is given, and as you can see that this is definitely a finite Fourier sine transformation. So we have fsn that equals to integral 0 to 2, that is the limit 0 to L. So it will be integral 0 to 2 capital Fx, then sine n pi x by L, and here L is 2 dx, n pi x by 2 into dx. Now putting the value of f of x here, so it will be 0 to 2 integral 0 to 2 x sine n pi x by 2 dx. Now for this integration we should apply the integration by parts formula. So keeping x as the first function, so it will be first function into integral of the second, that is minus of cos n pi x by 2 divided by n pi by 2. So here limit should be 0 to 2, that is, let it be in bracket, then minus integral 0 to 2 differentiation of the first, that is 1, integral of the second, that is plus cos of n pi x by 2 divided by n pi x by 2. So it will be 2 by n pi into dx, right? So now putting the limit, that is cos of n pi 2 by 2, that is cos of n pi. So cos of n pi, and then the lower limit is 0, and so it should be 0 here. So we have So it should be 2x by n pi. Okay, let it be 2x by n pi minus 2x by n pi cos of n pi x by 2, and then plus 2 by n pi cos n pi x by 2, that is sine of n pi x by 2 divided by n pi by 2. So it will make, this is 4 n square pi square, and the limit is 0 to 2. Okay. So by putting x equals to 2, we have, from the first term we have minus 4 by n pi cos n pi, minus 4 by n pi cos n pi, and from the second term we have sine of n pi. Sine n pi means 0, so we can remove that value, and after that for the lower limit of 0, this first term will give a 0 and the second term again will give 0. So the final value should be minus of 4 by n pi cos of n pi. So that is the value of this transformation. Is it okay? So I have explained the first part of the Fourier transformation, and this is the Fourier sine transformation. Let's move on to the second part, that is Fourier cos or cosine transformation. And here also the Fourier cosine transformation is also divided into two, that is the infinite Fourier cosine transformation, and the second one is a finite Fourier cosine transformation. So let's move on to discuss the Fourier cosine transformation. So we have B, that is Fourier cosine transformation, and for this we have again two parts, that is the infinite Fourier cosine transformation, infinite Fourier cosine transformation. So here also, if a function f of x is defined in such a manner that x lies between 0 to infinity, if the function f of x is defined in such a manner that x lies between 0 to infinity, then the transformation, that is fsn, is given this is not fs but fc, as because c for cosine. So it will be fcn, and that equals to integral 0 to infinity f of x cos nx dx, where again here also n is a positive integer. So fx is called as the inverse cosine transformation of fcn, and we can also find the value of f of x, and from this it can be written as 2 by pi integral 0 to infinity f of c n into cos nx dx. So the formula remaining the same, and this is how to find out capital Fx, or how to find out the Fourier cosine transformation Fcn. Okay. Is it okay? Okay. Now let's move on to the finite Fourier cosine. The finite Fourier cosine transformation. So here the function f of x is defined in such a manner that x lies between 0 and L. X lies between 0 and L. So here f of x is defined as in such a manner that x lies between 0 to L. So f of Cn can be given as 0 to L, then Fcn, then f of x into cos of n pi x by L into dx. When L equals to pi, again, if L equals to pi, or when L equals to pi, then Fcn equals to integral 0 to pi capital Fx cos nx when cos nx dx. Okay. So there are similarities between the Fourier sine transformation and Fourier cosine transformation. Now let's take an example. Let's take an example how to find out how to use this Fourier cosine transformation. And for this, I think example number 4, and so find the finite Fourier. Yes, and not clear. Today whiteboard is not clear. I think initially it was clear, isn't it? Is it better? It is not clear from beginning. But at the beginning, find the Fourier finite cosine transformation. Is it okay now? Is it okay? No, sir. Is it okay right now? Any improvement? Slightly. Okay, Madhumita has a question, sir, why we need to do Fourier transformation. Actually, the name suggests that why we need this type of transformation. In Laplace transformation also, we have to transform any function from one variable to another. And here also, in Fourier transformation, we can convert one function to the other. Actually, Fourier transformation as well as the Laplace transformation is suitable. Finds their applications in basically network theory and also in the communication. Actually, in communication, Fourier transformation is more needed, as because here we can transform one function from its time domain to its frequency domain. Actually, Laplace transformation can also transfer a function from its time domain to its frequency domain, but Fourier transformation is more applicable in the case of communication systems. So that is the importance of Fourier transformation or Laplace transformation. Now let us take one example. As I have told that now let's find the Fourier cosine transformation of x. So we have FCN. We have FCN equals to integral 0 to pi and then capital F of x, and f of x is x here. So x cos nx dx. So here we are going to find the finite cosine transformation of x. Okay. So we have to write fc equals to integral 0 to pi, as because the function is defined within 0 to pi. So the limit of the integration is from 0 to pi, and then x, that is the function itself, capital Fx, and then cos nx dx. Now on integrating by parts, we can write it as first function x, then integral of the second, that is minus of cos nx by n, okay, limit 0 to pi, minus integral 0 to pi, differentiation of the first, that is x, that is 1, then cos nx becomes 1 by n sine nx dx, right? So this is minus x cos nx by n, where limit stands 0 to pi, then 1 by n square, and sine, integral of sine becomes minus, so that this cos nx and the limit is 0 to pi. Okay? Oh, first function into integral of the second. So this will be sine nx. First function into integral of the second, that is sine nx by n. Okay. Sine nx by n. Now by putting the limit of pi, that is sine n pi means 0, and again for the lower limit 0, the value remains 0. So omitting this value, we have minus of 1 by n square into cos n pi, minus of cos 0, that is 1. So this will be okay. Okay. So this is the way we can find out the Fourier transformations of different functions. We can use it actually this transformation finds its application more in the communication system, as because in communication system we have to transfer a function from its time domain to its frequency domain, and there this Fourier transformation finds its application. Okay, now let's move on to the third part of the Fourier transformation, and that is the Fourier complex transformation. So the complex Fourier transformation is the third part of Fourier transformation. The complex Fourier transformation. Now the third part is complex Fourier transformation. Now the complex Fourier transformation f of x, here x lies between minus infinity to plus infinity. So here x lies between minus infinity to plus infinity, and it is defined as f of n integral minus infinity to plus infinity capital F of x e to the power I n x dx, where I is the complex number. Now here e to the power I n x is called the kernel of the transformation. Now the inverse transformation, that is capital F of x can be written as 1 by 2 pi integral minus infinity to plus infinity f of n, then e to the power minus I n x, and remember this will be dn. This will be dn, not dx. This will be dn. Okay, so this is the complex Fourier transformation. Here the function is defined in the limit minus infinity to plus infinity, and for this the transformation can be given or written as integral minus infinity to plus infinity capital F of x e to the power I n x dx. In many books you can find, or you may find, this is e to the power minus of I n x dx. It may be e to the power minus of e to the power minus I n x dx. Then you just look at this, that the inverse transformation here, it is also given as e to the power plus I n x dn. So both of this, that is, if you write f of x e to the power I n x dx, then you have to write f of n e to the power minus I n x dx, since it is the inverse Laplace transform. Or if you write this is e to the power minus I n x dx, then you should write this in this part, that is the inverse transformation, as e to the power plus I n x dn. So this is the way. Okay, this is the way we can represent the Fourier transformation. Right. Have you any queries? Have you any questions? Actually, I am running through a throat infection. So, if you have no question right now, I just end this class, and later on, tomorrow, I will conclude this topic. Is it okay? So today I have just introduced the topic Fourier transformation, and later on in tomorrow's class I will be continue from this complex Fourier transformation, and we will apply this complex Fourier transformation to find out some functions, Fourier transformations of some definite functions, some various functions. Okay. So goodbye.